Hey everybody, welcome. In this video, we're going to go over the gambler's fallacy. Alright, to understand the gambler's fallacy, we first have to understand at least a little bit the notion of independence. This is a notion that we'll work through more formally and more rigorously when we do probability theory in a couple weeks, but we can gain an intuitive sense of it already, just given what we know now. We'll say in general that propositions are independent, and sometimes we say statistically independent, probabilistically independent, evidentially independent. All of these things mean the same thing. We'll say propositions are independent just in case neither provides any evidence for the other. So independence is a relation that holds between different propositions or different statements, right? So we can think of this in terms of the notion of inductive probability that we've already introduced in this course. We'll say that statements or propositions P and Q are independent when the following arguments have the same inductive probability assigned to them, right? One of them being an argument from P to Q, right? It's a one premise argument, asserts P, concludes Q, and the other being a one premise argument that assumes the opposite, assumes not P, concludes Q. Now, when these two arguments are of the same quality with respect to their inference, we say that P and Q are independent of one another. So, here's an example where we plausibly have independence, right? Take an argument. I drank a glass of water today. Therefore, Dwayne "The Rock" Johnson will be elected president, right? Consider the competing argument. It has as its premise the opposite of what we had as the premise in the first argument. I did not drink a glass of water today. Therefore, Dwayne "The Rock" Johnson will be elected president. Now, truly, these are both pretty poor arguments. But they also show that we have independence between the premises of these arguments and the conclusion, right? Because me drinking a glass of water today provides no more support for the conclusion that The Rock is going to become the president than the proposition that I don't drink a glass of water today, right? Me drinking a glass of water is independent of whether or not The Rock becomes president or not. It provides no support for that conclusion, okay? Or at least no more support than its negation would provide for that conclusion. So this is an example of statements that are independent of one another. Here's a case where we'd plausibly have dependence, right? Consider this argument. Dwayne "The Rock" Johnson will be nominated by a major party for president. Therefore, Dwayne "The Rock" Johnson will be elected president. This is intuitively a much better argument, right? And consider the competing argument now with the negation. Dwayne "The Rock" Johnson will not be nominated by a major party for president. Therefore, Dwayne "The Rock" Johnson will be elected president, right? And truly, the first argument is much stronger than the second, right? That's because there's dependence between the proposition that The Rock wins a major party nomination and the proposition that The Rock becomes president, right? If we are given as a premise that The Rock will be nominated by a major party for president, it supports the conclusion that he will be elected president. Whereas the negation of that premise, namely the proposition that he will not be nominated, fails to support that conclusion that he will become president. So we have a clear dependence here, right? In general, if someone's nominated by a major party for president, that is evidentially relevant to whether or not they'll become president. All right, so now that we understand the notion of independence and dependence, at least at an intuitive level, we can state what the gambler's fallacy is. Right? The gambler's fallacy is a bias or an error in human reasoning that occurs when we see dependence between propositions when there's really independence between the propositions, right? Or we treat propositions or act as if they were dependent when in fact they're independent. So here's a sort of example. Suppose that I flip a fair coin, that is one that's always equally likely to land heads versus tails. That's what we mean by a coin being fair. Anytime I flip it, there's a 50% chance it lands heads and a 50% chance it lands tails. So suppose I flip a fair coin 5 times. Suppose that the first 4 flips are all heads. So I get heads, 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 heads. Now, how likely is the next flip, that 5th flip, to be a heads? Well, the correct answer should be fairly apparent here from the fact that we've said this is a fair coin. Namely, it's 50-50 whether it's going to be heads or tails next time. But those that fall prey to the gambler's fallacy will answer that tails is actually more likely than heads because we're due for tails, if you will. Right? We've had 4 heads. We know that the coin is a fair coin, so it's 50-50 heads, tails. So we expect there to be at least some tails in there within the 5 tosses, right? If we've gone through 4 heads, we're like, oh, we're coming due on a tails now. Right? So someone who commits the gambler's fallacy would look at these 2 arguments. First argument, we've seen 4 heads, therefore the next toss will be tails. And they'll judge that to be a better argument than the argument, we've seen 4 heads, therefore the next toss will be a heads. Right? They think seeing 4 heads provides some support for thinking that next time we're not going to get heads. We're going to get tails because things need to even out. Right? So we want to have roughly equal proportions of heads and tails. So someone who gets the gambler's fallacy again says the first argument is better, when in reality both arguments are really equally good. We should assign them equal inductive probability because getting 4 heads is independent of whether the next toss will be heads or tails, given that we've said the coin is a fair coin, right? If we were to flip a coin a ton of times, maybe thousands of times, and we looked for all the times where we saw sequences of 4 heads, and then we looked to see in what proportion of those cases do we get a tails after it, and in which proportion of those cases do we get heads after it, we would see that in about 50% of the cases we'll get heads after, and in about 50% of the cases we'll get tails after, right? That is, this argument on the left will lead to from a true premise to true conclusion about 50% of the time. Same with the argument on the right. It'll lead from a true premise to a true conclusion about 50% of the time. So we should be assigning these the same inductive probability. But if we fall prey to the gambler's fallacy, we'll assign them different inductive probabilities. We'll assign more inductive probability to the argument on the left. Now, what could explain why we tend to commit the gambler's fallacy? Well, one proposal is what's known as the representativeness heuristic. And this was an idea that came up from Daniel Kahneman and Amos Tversky, who are 2 of the most famous figures in psychology and behavioral economics in the past 30, 40 years. It was really in the 70s, so I guess that's maybe it's getting closer to 50 years now. But it was in the early 70s that they started talking about the representativeness heuristic. Basically, what they did in their program was they came up with a bunch of heuristics and biases that they observed humans to employ in the course of their reasoning and making judgments about the world. And right, a heuristic right here is really a sort of rule of thumb that humans tend to use. That's not necessarily good all the time, but maybe it is good in certain contexts. The representativeness heuristic is like that. It's maybe good in certain contexts, but it can also possibly lead to errors like the gambler's fallacy. So what is the representativeness heuristic? Well, it's a rule of thumb, and we tend to use it when we're estimating probabilities. So according to this heuristic, the probability of a particular outcome of a process, like the process of flipping a coin a bunch of times, is determined by how representative that outcome is of the process. Okay? So in the coin flipping case, a long string of heads is not judged representative of the process of flipping a fair coin. Because if we're flipping a fair coin, we associate that with evenness, right? Evenness between heads and tails. So we expect any sample that we get or any outcome of, some string of heads, or some string of coin tosses we've done, we expect there to be about an even proportion of heads to tails in there. So say we flip a coin 5 times and we get 3 heads and 2 tails. That seems more representative to us than a time where we flip the coin and we get all heads or all tails. Okay? So something like getting all heads, 5 heads in a row, is judged as less probable than getting 4 heads and a tail, because the second one, the getting 4 heads and tails, is slightly more representative of the process of flipping a fair coin than the first one, or at least so we think, right? And this could account for the gambler's fallacy, right? It could account for why we judge the first argument here, the argument on the left, to have higher inductive probability than the argument on the second, if we commit the gambler's fallacy. Let's consider another example of something like the gambler's fallacy that doesn't involve flipping coins. So suppose that every time one gets pregnant, there's a 1% chance of having twins, right? And this is an independent process, right? So every time you get pregnant, there's always that 1% chance that it's going to result in, or that you're going to be bearing twins, and there's a 1% chance that you're going to be bearing a single child. Now supposing that one gets pregnant twice, it's very unlikely to have two sets of twins, right? Because it's only 1% chance on each time that you're going to have twins. So very unlikely then, or very unrepresentative, we might say, that you'd have two sets of twins, right? Having two sets of twins would be unrepresentative of pregnancy in general, given how unlikely that is. The gambler's fallacy might then lead us to suppose that it's especially unlikely for someone who has had twins to have twins again, right? So supposing that you've had twins, we think it's less likely that you'll have twins again than that somebody who didn't have twins would have twins the next time. Because having two sets of twins in a row seems unrepresentative of pregnancy. But assuming independence, this would indeed be fallacious, right? The probability of being pregnant with twins, given one previously gave birth to twins, is the same as the probability of being pregnant with twins, given one was previously pregnant with a child, right? This is given that independence assumption, which is a sort of empirical assumption here that we could figure out whether that's really plausible by looking at the data. So the basic problem here is that unrepresentative runs of an independent process are not corrected in any systematic way by future runs of the process, and yet we tend to think that they are. When I flip the coin 4 times and I get heads 4 times in a row, I think, oh, we need to somehow correct for that or balance for that by getting more tails now. But that's not really what happens. Rather, the unrepresentativeness of small samples is simply diluted in large enough samples. So I flip that coin 4 times, I get the 4 heads, I keep flipping it. There's not going to be any systematic tendency for me to get more tails in the future. It's just that I'll get some runs of heads again, I'll get some runs of tails again, right? If the coin is really a fair coin, I'll get some more evenly spread runs. And once I've gone through a large sequence of runs, then everything will sort of be washed out or diluted, and I'll get about 50% heads, 50% tails. That's what we would expect in a sufficiently long sequence. So that's how things really work, but it's not the case that when I get a sequence of heads, then in the future somehow it's biased now towards tails, or I get a sequence of tails, and now in the future it's somehow biased towards heads, right? And yet we tend to have that sort of thought that that'll happen, and that leads to the gambler's fallacy. Now it's important to note here that sometimes a chance event is dependent upon a previous one. So for example, this often happens in card games when we're drawing cards without replacement. I draw a red card from the deck, right? That ups the probability that I'm going to draw a black card next time, right? Because now there's one less card in the deck, right? So in those sorts of cases, we should revise our probability assignments in light of previous results, right? The point here is just that we need to be careful about assessing the independence and dependence of chance events, right? Sometimes propositions or statements about events are independent of one another, and sometimes they're dependent about one another. And we're not always super good just on the basis of our initial instinctual judgments. We're not necessarily super good at telling that. So we have to be careful about that. All right. So this concludes our video on the gambler's fallacy. Please complete the participation poll for this video, and I'll see you next time. Thanks.